Okay, so now let's look at the Grassmann manifold. Okay, so this is denoted Grass Pn. Okay, so let n be a positive integer and p also be a positive integer less than or equal to n. Okay. All right, then this Grassmann Pn, all right, denotes the set of all p-dimensional subspaces of Rn. Okay, and we're going to construct a one-to-one correspondence between the space of the Grassmannians with the quotient manifold, or some quotient manifold that's like of Rnp, right? So we want to construct a one-to-one correspondence between Grassmannians and the quotient manifold of Rn cross P. And in so doing, it's like this endows, it's like the Grassmannians, it's like with a matrix manifold or matrix quotient manifold structure. Okay, all right. So the way we're going to do this is we're going to start with the non-compact Stifle manifold. So start with the non-compact Stifle manifold. Okay, which is Rn cross P star. So this is just a set of n by p matrices which are of full rank. With full column rank. So as you might expect, then what that means is that the columns, it's like of these n by p matrices span a p-dimensional subspace in Rn. Okay, so that's, if you will, how these two things are going to be related to each other. And so each of the elements of the non-compact Stifle manifold give you a particular representation, if you will, of a p-dimensional subspace. But of course, there's more than one possible representation, just as there are more than one possible choices of bases, right, more generally. Okay, so let's define an equivalence relationship now on this non-compact Stifle manifold, which would then give you the Grassmannians, right? So let tilde be an equivalence relation. On this non-compact Stifle manifold, which is defined by the following, that two matrices are equivalent to each other if and only if their spans are the same. Okay. So where the span of X denotes the subspace spanned by columns of the matrix X, which is in, again, this non-compact Stifle manifold, which means, again, these are linearly independent sort of column vectors, if you will. Okay, that's equivalent to saying that it has full column rank. Okay. All right. So the fibers of the span are equivalence classes. The equivalence relationship, and since the span is onto the Grassmannians, which are the set of just p-dimensional subspaces, right? So it follows that there's a one-to-one correspondence that, well, the span induces a one-to-one correspondence between the Grassmannians, the Grassmann manifold, and this quotient manifold, which is, again, this non-compact Stifle manifold quotiented by the equivalence relationship, which is induced by the span operator. Okay, so let's try to denote this with a diagram. Right, so you have R n cross P star, non-compact Stifle manifold. There's a natural projection by the equivalence relationship. Okay, and there's a projection just by the span to the Grassmannians. And then these two things are just related to each other. Okay, so let's just put a little bit of notation here. Okay, so if we have a matrix, and there's a subspace curly X is the span of X. Right, we say that curly X is the span of the matrix, and X spans the space X, or that X is a matrix representation of the subspace curly X. Okay, and then the set of all matrix representations of the span of X, right, is the equivalence class. This is the projection. Which is pi inverse pi of X. Okay, all right. And I can write what that is. So pi inverse pi of X is a set of X times M, where M is in the general linear group of dimension P. So these are P by P invertible matrices, okay? And I can write this as X times GLP. And the reason, of course, is that if you have a particular basis, it's like for this p-dimensional subspace, you can convert to another basis by some sort of invertible transformation, which is again in GLP, right? So, so in light of this, right, you oftentimes refer to this equivalence relationship now in terms of this general linear group of dimension P. Okay. So, so in view of this observation, right, you can write that the Grassmannians are sort of isomorphic to the following, right? Rnp star. So this is again this non-compact Stifle manifold quotiented by the general linear group of dimension P, right? And then here now you're really sort of using the notation it's like which is associated with group theory. It's like and quotient groups, right? And you can do this because it's like if you think of matrices, right? The composition, the matrix multiplication is a group operation, and you have that kind of quotient group. Okay. So. So you can show that this quotient is actually a quotient manifold. So let me just state the proposition. Right, this is the Grassmann manifold. So the quotient set Rn cross P star, quotiented by the general linear group of dimension P, right, admits the structure of a quotient manifold. Well, admits a unique structure of a quotient manifold. Okay, and you can show this. It's like by using the previous propositions we had. It's like having to do with properties of the graph of the equivalence relationship. So let me sort of just not really prove it, but let us just sort of remark that one proves this. By showing that the graph of the equivalence relationship, right, satisfies the three conditions of this previous proposition, it's like which we discussed, right? Okay. All right. So I don't really want to go too much into details. It's but suffice to say, you can endow the Grassmanns. It's like what with a quotient manifold structure. Okay, so endowed. So the remark is that endowed with this quotient manifold structure, right? Then the set Rn cross P star quotiented by general linear group of dimension P is called the Grassmann manifold. Which again consists of p-planes in Rn. Right, and is denoted by Grass Pn. Okay. So as a special case, is p equals to 1, right, where Grassmann 1p, 1n, right, is just the real projective plane of dimension n. Okay. Right. Okay, and then you can check that the dimension of the Grassmann manifold, so the dimension of the Grassmann manifold, okay, is can be obtained by information about the dimension of this graph, okay, and the dimension of Rn cross P. Okay, so it's 2 times the dimension of Rn cross P star minus the dimension of the graph of the equivalence relationship. Okay. So this is 2np minus 2np minus n minus p times p. So this is going to be n minus p times p. Okay. All right. So anyway, so this gives you sort of several ways of thinking about the Grassmann manifold, right? Either in terms of equivalence relationship or through this transformation. It's like of the general linear group of dimension p. So if you will, it's like this is given a particular matrix representation. It's like of the p-dimensional subspace, right? You can do this change of basis in some sense, right, through this action into general linear group, right, and that gives you a different representation. So the orbit, if you will, it's like of a sort of full rank n, it's like n by p matrix, right? It's going to then give you, it's like the set of all n by p matrices which generate the same sort of p-dimensional subspace. Okay, so that's where that notation comes in, and then you can evoke sort of this fairly general result. It's like we have, it's like having to do with looking at properties of the graph or the equivalence relationship to show that this indeed has the structure of a quotient manifold. Okay, and then if you recall, similarly, it's like the result on quotient manifolds, it's like also tells you something about the dimension. It's like in terms of 2 times the dimension of the space, it's like on which the equivalence relationship is defined, minus the dimension of the graph, right? And then some sort of calculations, it's like give you that dimension. Okay, so so that gives you, it's like the kind of manifolds we're going to primarily be looking at, which are either embedded manifolds and quotient manifolds. And the next thing we're going to talk about, again in anticipation of the fact that we're going to do optimization of all this, is we're going to talk about tangent vectors and then introduce various notions of measuring the length of tangent vectors through inner products and more generally through some sort of Riemannian metric. So let me just stop here for now.